Okay, so we are in the third lecture of the discrete structures class, and let me give you an overview of what we have done so far. We have we started by defining a statement which has truth value. It must be either true or false, um, which may be determined by an oracle. Oracle का concept हमने थोड़ा सा define किया, and then we talked about compound propositions. We talked about using logical operators like and or to construct slightly more complex propositions from simple propositions, exclusive or and negation as well. Then we talked about conditional propositions, which were in the form of if P, then Q, and then we see when are these conditional propositions true. Okay, if we know P is true in Q is true, then it's true. तो उसके जो four cases we saw them. We talked about biconditional propositions. We define converse from a given conditional proposition. We define contrapositive. We define inverse. We saw that a conditional proposition implies the contrapositive, but it does not necessarily imply the converse or the inverse. Excuse me. Then we defined a couple of things. One was the tautology, which is that statement which is always true. We define a contradiction, which is a statement that is always false. And these were the forms of the tautology and the contradiction. We defined what it means for two statements to be equivalent. We said that two statements are equivalent if their two tables are exactly the same. Okay, but then we saw that, that to show that two statements are equivalent, it's not necessary that you make the whole table of it. Okay, it's possible that you replace few things, you apply the laws that we saw of the proposition. De Morgan's law, we saw De Morgan's law, and we saw the laws. Maybe they are here somewhere. Where are they? Yeah. Associative law, distributed law. We used a distributed law in an example. We also used the double negation. I think it's somewhere here. ये जो है, we saw this one, we saw this one, and we saw De Morgan. I think these three laws we used. You should familiarize yourself with other laws as well. So we did that. We talked about logical equivalence. Okay, we saw what the negation of a compound statement is, or that was probably the example that we used to introduce the De Morgan's law. And we talked about equivalence. We did this example. That's where we used the laws. Second De Morgan's law, first De Morgan's law, double negation, distributed law, identity law, commutative law. Okay. I hope you already went through some of this material in your book and are good. We then defined a new concept, which is the predicate logic, which says that instead of just making a statement which is either true or false, we make a statement which becomes true or false when we do something with, when we quantify it. Okay, we give, I think, 3 examples of quantification. This should be somewhere here. Where are they? Yeah, over here. So we say that when we replace a variable in a predicate with an exact value from the domain of that variable, we get the proposition. Similarly, when we say that this is a statement, let P be a statement, we say this is a statement for all values of x in the domain. Then this also becomes a proposition. That's the universal quantifier जो use कर रहे हैं. We are saying that the statement is true for all values in the proposition. Similarly, when we say that the statement is true for some values in the domain, then this is also a proposition, and this is true when the statement is true for at least one value in the domain of the variable. Okay, so these were 3 quantifying methods for predicates, which turn a predicate into a proposition. I think we have an example here that we can probably go through. Yeah. So any questions so far before we move on with the predicates? Anyone? All right, I think we are good. Are we good to go? I also wanted to mention something I forgot last week about these slides. These slides are actually made by a very good friend of mine, Dr. Wasim Abbas. He's teaching discrete math at Vanderbilt University. I think it's somewhere on the first slide. Yeah, so that's his name. These are really, I really like these slides. Okay, I'm a fan of these slides. So if you also like them, so it's not a bad idea to send him an email and just thank him that we are using your slides. And it's, I mean, I already sent him an email, and he's a good friend of mine. But if you want, do send him an email and just say thank you. Okay, so sort of, I think it would be good. All right. Okay, so here is our first example of turning a predicate into proposition. We saw this. Where is it? Yeah. Okay. So let's say a predicate statement says that a person is older than 30 years old. Okay. This is a predicate because as long as this variable remains a person, you can't say whether this statement is true or not, right? But when you, for example, replace this with a particular person, for example, अगर यहाँ पे मेरा नाम आप लिख देंगे, the statement becomes true, right? I'm older than 30. But this thing, this quantification is the first type of quantification, that you replaced the variable with one particular value in the domain. Okay, so this is first type of quantification. Here is a second type of quantification. I'm assuming कि इस variable की जो domain है वो ये है. Okay, it's everyone in this class. Okay, let's assume that that's the domain. Now, if I use universal quantifier and I say that all people in this class are older than 30, then this becomes a proposition. That's the important part. This is false, of course, but the important part is this now becomes false because the statement is not true for everyone in this class. Similarly, if I use the third type of quantification, which is that if I say that there is a person in a class who is older than 30, then this becomes an existential quantification of the predicate, and it still becomes a proposition with the truth value of true, because there is at least one person in the class. Okay. So this is what we saw last time. Three types of quantifications. You replace variable with a particular value. You say that the statement is true for everyone in the domain. And the third case, when you say that the statement is true for at least one person in the domain. Okay. You either say that it's true for some values of x, or you say that it's true for at least one value of x. Okay. It's the existential quantification of a predication. Okay, that's fine. Okay, so here's the thing. For an existential quantifier, this is how we write it. This is opposite and opposite directed E. Okay, so you write E like this. इसको अगर इसकी direction change कर दें, तो this becomes an existential quantifier. Okay, so for a statement, let's say the statement is p of x, and we want to apply existential quantifier on this, we will write there exists. That's how you read it. There exists an x, p of x. Okay, and you can think of this thing as a disjunction on proposition by replacing x with every variable, every value in the domain. Okay, so let's say your domain is x1, x2, x3, xn. Okay, and you want to say that there exists p of x. Then all it means is that you want to say that p of x1 or p of x2 or p of x3 or p of x4, so on, till you reach run out of the variables. Okay, the last statement will be p of xn. All right, so okay, there is an error here. Okay, forget about this. Okay, this is not what is written here. That's what it's written. Okay, so when I say that there exists x, p of x, all I want to say is that p of x1 or p of x2 or p of x3, and continue until you run out of the variables. Okay.
How is this different from what we just checked above? Because all of these are true either way. So is it like one of the x's in the domain is true, or
yeah.
all?
So remember when we made a compound proposition by using or variable, when we said that p of x or p of x true, then this statement is true when either x1 is true or x2 is true, or at least one of them is true, right? The statement becomes true whenever there is at least one variable in the or statement for which one instance of the variable for which the statement is true. Then the or statement becomes true, right? So the or statement is true when only one of the one of the instance makes your statement true.
So it doesn't necessarily matter that more than one x's are true, because if even one of them is true, then we don't care about the rest.
Yeah, perfect. That's exactly what I mean. So if you have a statement or uski jo variable ki domain hai, it contains, let's say, 10 variables, and your statement is true for only one of them, then the statement that says that there exists an x p of x is true. If it's true for two of them, it's still true. We don't care. अगर एक के लिए true है, तो फिर the statement, this thing will become true. ये जो हमने existential quantifier के साथ statement बनाई है, then this becomes true. Whenever there is at least one of them. Okay? अगर एक से ज़्यादा है, we don't care. It's still true. This becomes false when the statement is not true for any one of them.
Yes, I understand.
Awesome.
Sir, these statements are always propositions, right? True or false here.
So when you say this thing, when you replace p of x1, you replace x with a particular value, this thing becomes a proposition. Okay. When you write this existential quantifier with your statement, this thing becomes a proposition. Okay. But if you just write p of x, then this is not a proposition.
Got it.
Great. Awesome. Okay. Here is the second quantifier that we saw, which was that you say that for all of x, p of x. Okay. You can think of this as conjunction, which is going to say that the statement is true for p of x1, and this is the critical part. Now you and it. Okay. This is a conjunction now. And this statement is true for x2, and it's true for x3, and it's true for x4, and so on until you reach the end of the domain. Okay. So when I say that for all x, okay, this is how you read. This is the inverse A. Okay. A ko apne ulta kar diya, and you read it as for all x. Okay. For all of x, p of x is a universal quantifier, and it says that the statement is true whenever the statement is true for every instance of the variable. जी बोलें.
सर ये अगर कैमरा रिकॉर्ड नहीं तो ऑफ कर दें, इंटरनेट का इशू है तो वो लैग करती है वॉइस में.
Okay. Ubed, is it a constant problem with everyone?
Sir, it is a problem for me, लेकिन I don't know. यहाँ पे कुछ complaints हैं comments में.
Okay.
So मेरे साथ भी यही problem है.
You want me to turn off the video?
Yes, sir, I guess.
Okay. Let me quit this thing. Let me know if it helps. Okay. All right, people. नहीं मेरे इंटरनेट का प्रॉब्लम तो नहीं है. Let me see. Let me.
सर ये मोबाइल डाटा पे शायद इशू आता है.
Let me change the. So I might be disconnected for about 10 seconds. Okay.
Sir, ये
so bear with me.
मोबाइल डाटा में.
All right. Can you guys hear me now?
Yes, sir.
All right.
Yes,
let's go on.
sir.
Okay, so when I apply the universal quantifier, and I would like to say that for all x, p of x, or what it means is that I am saying that the statement is true for every instance of the variable in the domain, जो मैंने define किया, okay? And that's written here for all x, p of x is equal to का मतलब ये है कि ये दोनों statements equivalent है, okay? These two statements are equivalent. Is equivalent to p of x1 and p of x2 and p of x3, so on until p of xn. Okay. That's the universal quantification of the conjunction. Is everyone good?
Yes, sir.
Any questions? Okay, let's move on. So once again, for all is a universal quantifier, and that's the symbol of for all, and that's how we write it. For all x, p of x. There exists as is an existential quantifier. This is the symbol for it, and that's how you write it. For there exists p of x. Okay. Okay, let's move on. I think we have seen examples. Okay. To prove a universally quantified statement, so to prove something like this, if some statement says for all x, p of x, to prove this statement, we need to show that the statement is true for all possible values. Okay, so we will have to prove that the statement is true for px1. We will have to show that this is true for p of x2, and so on. Okay, we have to show it for everything in the domain of x. Okay. To disprove a universally quantified statement, to show that a universally quantified statement, again the same statement, okay, we suspect that this statement is not true. Okay, if this statement, we believe that this statement is false, so all we need is that we need to show that there is one value for which this is false. Okay, all we need to show is that there is some pxi जिसके लिए ये false है. Okay, so if you want to prove this true, you are going to have to prove it true for every instance or every point in the domain of your variable. Okay, but if you want to disprove the statement, if you want to show that the statement is wrong, all you need is you need to show it false for only one state, for only one value in the domain of x. Okay, does this make sense? Are we good?
Just like an AND operator.
Just like an AND operator. Just like an AND operator. जैसे हमने यहाँ पे देखा था. Universally quantified statement is another way to just write an AND operator. Good. So,
सर
yeah.
क्वेश्चन मतलब ये एंड ऑपरेटर और मल्टीप्लिकेशन और जिस तरह ये भी आपने प्रेडिकेट्स पढ़ाए हैं, ये सारे एक ही चीज हैं, तो ये सारे मतलब इनको इतना डिफरेंट तरीके से क्यों भी बताया जा रहा है एक एक करके? मेरे ख्याल से ऑपरेशन तो ये बिल्कुल सेम नहीं है.
Sure, बिल्कुल. So here's the thing. The thing is, I want to make a statement like, I think मेरे ख्याल में यहाँ पे example में भी है. Okay? So for example, here look at this statement. I want to say that for all positive integers x square is more than x. Okay, this is what I want to say. Okay, if I want to say this in terms of integers, what would I need to say? I would have to say that 1 square is more than 1, and 2 square is more than 2, and 3 square is more than 3, and so on. So this is an infinitely long statement, proposition. And here I have a very nice, concise way to write it down, right? So this is sort of a language of mathematics that we use to write otherwise very complex statements, which are probably not. So for example, AND operator अगर आप सिर्फ use करना चाहेंगे, तो you can't write this statement because this is an infinitely long statement. But if you write it like this, you use the universal operator, you can write it for all x square is more than x, and x is a positive integer, right? So this is a sort of a simple language to write the same thing. Does it make sense?
Yes, sir. Thank you.
Awesome. Good. Great. So we have this statement which says that for all x square is more than x, where x is an integer. The statement is false because I can find one particular value in the domain, ये मेरी domain थी, which is x equals 1, when this statement is not true. Okay, so for p1 this is false, right? For p1 this would be false because for p1 1 square is 1 and it's not more than 1. Okay, make sense? So the statement is false, and to prove it false, all I needed to do was find one example where this is false. Okay. Now, if I want to say that for all x, after finding this out, I want to modify my statement, and I say that for all x, x squared is more than x, where x is a positive integer greater than 1. Okay, so I'm saying that statement is true for 2, 3, 4, 5, and so on. Okay, the statement is true, but I'm not giving you a proof here. Okay, to prove it, what you need to do is you need to show that the statement is true for every possible value in the domain of x. Okay, which is not easy. Which is you need to be slightly clever because there are infinitely many things in the domain of x. Okay, I'm holding on to the proof for now. Okay, but the point here was that if you want to prove something false, it's sort of easy. Okay, if the statement is actually false, all you need to do is you need to find out one example which lies in the domain of the variable where the statement is false, and you're done. Okay, but if you want to prove something true, it's slightly tricky. Okay, you will have to prove it for every value in the domain.